So that's what's being captured. Great. So should we go ahead and get started? Hopefully you got your arrays of benzene to display yesterday. For the homework assignment today, you'll be able to use that program to get at the coordinates for your benzene dimer if you want to go that way, to be able to say, okay, I really did create this, create these coordinates from Python. So today we're going to start going through a discussion of sort of electronic structure methods or biomechanical methods. I always have a tough time saying electronic structure, because if there's one thing that you don't know, it's the structure of the electron, right? You know spin, you have probabilities, but you don't really have structure. But that's what the community uses to describe electronic structure approaches, and so we'll use it. So what do you want to do with quantum mechanics, electronic structure techniques? One area where electronic structure plays a role is in the development of force fields for use in molecular dynamics simulations. You can get at the partial charges that are used for, say, a novel combination that you're studying in your system. And we'll go through the process that one does in Gaussian to get at the types of charges that are used in amber simulations. You can get at van der Waals interactions, try to understand more about the sort of weak interaction that is essential for holding species together in the condensed state. Challenging to obtain a reasonable van der Waals parameters, but it's possible. You can get at functional forms, whether the shapes of stretch, bend, torsion, what do they look like? If you wanted to, for example, consider a situation where you're going to break a bond, what is the shape of that surface? And then get at things like distances, angles, torsions for structures, again, for something that is novel, that's not a part of one of the standard force field models like amber. You can also get at just molecular structure, where you might have an unusual bonding or intermolecular interaction, and you want to understand what it's due to, what's going on there, and your second homework problem that you're going to be getting is of that ilk. We're going to use electronic structure to try to understand the bond angles that are observed in some simple hydrocarbons or hydrogen-containing species. So group 5 and group 6 compounds, what is the nature of the bond angles in those molecules? Get that structure, we take the derivative of the energy with respect to nuclear displacements, and then we can look at the wave function, we can look at the electron density to get an understanding about what's going on. We can also then use the second derivative of the energy with respect to nuclear displacement to get at vibrational interactions. Again, those vibrations could feed back into a force field model. Use electronic structure to get at transition states. Both obtain the magnitude of the transition state as well as trying to understand why a barrier is small or high, when we change things, what goes on there. And again, for that information, we use the second derivative of the energy to get at the shape of the potential surface or the transition state. You're not at a minimum, you're at this sort of pass connecting reactants and products, and the second derivative of the energy can get at that information. And so one of your homework problems tomorrow will be obtaining a transition state for a small system. You can also get at excited states with electronic structure techniques, and Martin's going to be talking about that on the day 4 or Friday of this week. You can also get at weak interactions, things like magnetism, and we'll be looking at for one of your homework problems, a system with an unpaired electron or two to be able to see how one analyzes that kind of system. I haven't looked at the surveys, but how many of you have had some quantum mechanics? Okay, most people, but that's all right. We're going to just do a quick scan before we go through how to use it. So at the end of the day, you'll be able to use a program called Gaussian to get at an electronic wave function, be able to optimize the geometry for a molecule, and then when we look at the results tomorrow, understand that all methods aren't created equal, and you can get the wrong answer pretty easily, or you can get the right answer pretty easily. But it doesn't matter what you do. Today, what we're going to be using is a Gaussian on the cluster, Gaussian 09. We'll also be looking at some of the results, and I'm going to try to use a new web-based program for doing the display and building molecules. If that ends up failing, we'll resort back to using Gauss view. Problem with Gauss view for us is that we only have a site license for Macintosh computers. So if you're sitting in front of a PC, it would be perfectly useless. And it's fairly pricey to get a new license for it. And, last summer, a couple of guys, one actually rented a bike, rode down to Best Buy, and bought a new Macintosh to be able to use Gauss view for this class. He rolls in the next day, and it doesn't work. It's a bummer. He liked the computer for the rest of the summer. I think he was glad he got it, but the version of a Gauss view that we have doesn't run on Sierra. They didn't have a version of Gauss view that would run on Sierra until just a few months ago. It was going to cost us $6,000 to get it. We haven't worked up the courage to do that yet. And so we're going to try to avoid using Gauss view. But if I panic, we'll go back to it. Another alternative is Avogadro. You can download Avogadro from a site. If you do Avogadro electronic structure in Google, you'll get to the site, and they have Windows, Mac, and Linux versions of Avogadro. It's a perfectly fine program. I find the builder a little sort of cumbersome, and if I download it, it overrides my use of the Crystal Maker software So if I try to fire up a crystal maker, I get Avogadro. No, if I click on a crystal structure fires up Avogadro. And I prefer crystal maker for looking at crystals than Avogadro. So, you know, but worst comes to worst, you know, you're having a tough time. That is an option that's available out there. So in class, we're going to just basically quickly review a little bit about quantum mechanics, about wave functions, and then we'll go ahead and do some calculations on benzene, where we'll optimize the geometry for benzene. We'll look at the molecular orbitals for benzene, and then we'll develop the mapped electrostatic potential, be able to look at what parts of benzene are positive and what parts of benzene are negative visually, and then we'll run a little script that lets us calculate the partial charges that are used in amber for benzene. And then we'll also look at vibrational frequencies, again for benzene. Then the next thing we'll do is look a little bit at benzene dimer, because that is one of your homework problems. Each one of you is going to calculate one of two different conformations for benzene dimer using different density functional approaches. And then when we collect the results tomorrow, we'll see how they do at obtaining the energies and structures for benzene dimer. Any questions? Okay. So electrons, sometimes protons, act like wave-like particles. I prefer to think of electrons as just being electrons. You know, when you go through in freshman chemistry and you go through in quantum mechanics, you talk about the wave-particle duality and when is it electron, when is it, and it's like, it's just an electron, okay? That's just the way it is. And worrying about when is it electron or when is it a particle, when is it a wave, you know, just takes away from what's important about it. And so electrons, observable properties of electrons can be described by a wave function, and any observable in principle can be obtained, where all you need to know is the operator that you put in the integral over all space, and that integral is called the expectation value of whatever the operator is. And it's often written in this form, where we say that we have wave function, operator, wave function. We take this integral and shorten it down into this broadcat notation, because it takes a lot less time and energy to write that out than it does writing out the whole integral. This particular form for the expectation value turns out to be problematic if you're actually really using it to get at a real property. And so we tend to use this form where if your wave function is normalized, the denominator is 1, but the derivatives of the wave function aren't 1. And so keeping the denominator there is important. So the Hamiltonian or the operator of interest that to get at the energy of the system is a Hamiltonian. It's an expression of the interactions between particles in the system in terms of potential energy and kinetic energy terms. And so when I was talking about derivatives of this with respect to coordinates, it's actually derivatives of this expectation value with respect to the coordinates of the system. Okay, key observations, and something again that tends to be left out in early discussions of quantum mechanics is the fact that, because you do the harmonic oscillator and you do the rigid rotor and then you do the hydrogen atom, and then you move on. But if you want to think about systems with electrons, more than one, you need to remember that the wave function for electrons must be antisymmetric with respect to interchange of the coordinates of any pair of electrons. And so if we had a wave function representation for 3 electrons, okay, if we interchange the coordinates of the second and third electrons, that is, change what orbitals they're in, then the wave function must change sign. That's a property of, if you will, of the structure of electrons that we do know, that the wave functions, descriptions of electrons must be antisymmetric. And we use a determinant representation to construct antisymmetric wave functions, and they're called Slater determinants because a guy named Slater came up with the idea of using this representation to get at the antisymmetric property. Interesting thing about that antisymmetric nature of electrons is that's why you can't walk through a wall, okay, is the fact that the wave function has to be asymmetric, that these orbitals can be taken as orthogonal to each other, and that is the repulsive interaction that one sees or uses in molecular dynamics simulation. So that's one sort of key observation. Another observation is that if you're using the correct Hamiltonian, and if you're using a proper trial function, that is one that is normalized or normalizable, then the energy of that wave function is higher than the energy of the exact wave function. That sort of gives you some comfort in that, if you come up with a basis set, and someone says, gee, that's not as good as X, Y, or Z, all you have to say is, I get a lower energy. Okay, mine's better because I get a lower energy. Assuming you're using the proper Hamiltonian for the system, as we will see a little bit later when we get into density functional theory, we change the Hamiltonian. And so at that point, this variational principle, variational theorem, holds within the Hamiltonian that you're using, but you can't compare one functional to another functional based on total energy. So we use this variational theorem to find the coefficients in our linear expansion, in our basis set, and by taking derivatives of energy with respect to those coefficients. Script A out in front says that we have a product wave function that is anti-symmetrized. So you would, in principle, write out your wave function, put it in a determinant, permute all of those around, and come up with the correct wave function. Take that anti-symmetrized wave function, evaluate its expectation value. Now, you almost never do that. Your energy turns out to be a simplified result, but underneath it is the fact that the wave function has to be ultimately antisymmetric. Okay, so basis functions. Now, when you look at results of electronic structure calculations in the literature, there are sort of two sets of acronyms that you run into that Yeah, they don't make any sense. Okay, they're just names that people came up with, ways of thinking about it. But basically, you could take your orbitals as an expansion in spherical harmonics, where you have the angular dependence of the spherical harmonic, you have an exponential function, you have this little short power series, that if you've gone through and solved the hydrogen atom, you've gone through and yeah, you have these B coefficients that you can determine analytically. You could do that, and for the 1s function, the hydrogen atom or 1s function has this form properly normalized. Uh, you could keep this series there, or you could say, well, I'm just going to do this expansion in R that goes up to L and let variational principle find these coefficients for a molecular system. If you were to do that, those functions are called Slater functions, again, for the same guy named Slater who came up with the Slater determinant. He was one that suggested that one use this sort of representation. Unfortunately, the intervals, the two electron intervals, interaction between electrons, those intervals are very time consuming, i.e. back in the day when you had to pay for computer time, very expensive, or back in the day when you had to do this by hand, very tedious to evaluate. Another guy suggested, a guy named Boyes, suggested he was into statistics, quite familiar with the properties of Gaussian functions, where you have, instead of e to the minus r, it's e to the minus r squared. And he suggested, wow, those intervals are a heck of a lot easier to evaluate. And why don't we use those instead? He published a couple of papers suggesting it, and then went back off into statistics. Now, they're not called Boyes functions, but in terms of what's actually used, these Gaussian functions are the far more common type of basis set. So for 1s for that, instead of this form, it's again normalizable, and we use e to the minus zeta r squared for that function. They're not solutions to our 1 over r potential, but a nice property about a product of Gaussians that are centered in different places, okay, is that you can take that product of Gaussians, grind through a little algebra, and end up with another Gaussian. So any combination of Gaussians at different places gives you a Gaussian. And so you could have an interval that's over 4 centers that collapse to 1 center. And that's a pretty nice property. Gaussians also are very amenable to quadrature, so numerical evaluation, and so that tends to be what we use. Question that comes up associated with this is, well, if I can describe the 1s function of hydrogen with one Slater function, how many Gaussians does it take? If it took, 100 Gaussians, this equivalent one Slater function, then the trade-off, the cost, could be different. But it turns out that it doesn't take very many, and so what's plotted here is a actual exponential function, the actual Slater function, and then the total energy for, say, 1 Gaussian, 2, 3, and 4, where this is in atomic units, where the energy in atomic units is in Hartrees. You take a number in Hartrees and you multiply it by 627.5, and that will convert it to kcals. And so 0.42 is in error by 47 kcals. You put two functions, and you can see here that the one function, the one Gaussian, looks like a Gaussian. It has a zero slope at the origin, whereas the exponential function doesn't go to zero. The slope doesn't go to zero at the origin. You add in a second Gaussian, and it comes in to improve the description of the cusp. A third Gaussian, a fourth Gaussian, and you start approaching the correct answer. By the time you've gotten to 10, you essentially have the exact answer for it. Practically speaking, when one does calculations involving hydrogen, one typically uses this four-function representation. It's sort of, by and large, good enough. Okay, the energy if you have a system, product of orbitals, put two electrons in each orbital, you end up with an expression where each electron sees each other electron with a Coulombic interaction, electrons being negatively charged. There's this Coulombic repulsion between them. Each electron sees all of the nuclei. You put that into this one electron term, and each electron has an associated kinetic energy. But because of the Pauli principle that says that wave functions have to be antisymmetric, if you exchange the coordinates of a pair of electrons, the sign has to change. We end up with this extra set of terms in the energy that are called the exchange. Now, they could have been called permutation intervals. Okay, they could have been called, Pauli principle intervals, but they're called exchange intervals that are associated with these permutations. If we look at this energy expression, all Coulombic interactions are repulsive. All two electron intervals are positive, and so this exchange actually lowers the energy of the system relative to a more classical or electron density description of it. Okay, so this is just combining some terms. Take the derivative of the energy with the denominator around, take the derivative of the energy with respect to these expansion coefficients, and we end up with a different variational equation that is a one electron variational equation where the electron sees, again, one electron potential, and electron sees Coulombic interactions and exchange interactions. And so this is a one electron problem, but it's in the field of all of the other electrons in the system. Okay, so moving right along, density functional theory, which is dominantly going to be what we're going to be using. You're going to probably do some CAS stuff, right? Yeah, but which is not a density functional approach. But density functional theory has pretty well taken over what people tend to use for doing electronic structure calculations. And so we want to describe a little bit about that. So if we start off with this Hartree-Fock energy expression here, just written it out again. The challenge in this is that is computing these Coulombic and exchange interactions. The Coulomb term is expressible in terms of electron. We've described it in terms of an orbital. We do the expansion functions pretty big in terms of number of terms. Okay. The exchange also can be expanded in terms of these two electron intervals. Okay. So if we look at this Coulomb operator, we can see that we have an integral over basis functions, and we have an integral over an orbital. That orbital product is a density, and we can sum all of these individual density terms. And so instead of having a n to the fourth, if we know the density, instead of evaluating n to the fourth terms, we only really have to evaluate n squared terms. Change or okay, so in this model, and it's like this is really intimidating. In terms of if you actually thought about actually computing this. The exchange energy, exchange correlation energy, it starts off with Slater exchange. That's the rho to the 1/3. Okay. It adds on a piece of the Hartree-Fock exchange. So it's A times this, 1 minus A times that. It's about 25%. It adds in an additional exchange term because it's not rho to the 1/3. Becky came up with an alternative exchange model and adds that on. So we have one parameter, two parameters. The third parameter is this electron correlation. There's the Li-Yang-Parr correlation piece times C, 1 minus C times A. Oh gosh. There it is. I couldn't remember their names. Vasco, Wilk, and Nusar exchange. If you think organic chemists are bad in terms of name reactions, the theorists also. I mean, it's like the name doesn't mean anything. It's just a name, but it's associated with the people who developed it. So this Becky 88 exchange has rho to 1/3. It has a cinch of the density in it, and a log, and just all kinds of stuff in there. The correlation term, actually, Li, Yang, and Parr, they get the lip, but they didn't actually come up with a model. Collet and Salvetti actually came up with the original model, but they were, from back basically day one, people realized that the results from a Hartree-Fock calculation weren't really very good. And so this electron correlation problem has been a struggle forever and still is. But in 1975, these guys came up with this model for describing correlation and expanded it out. Li, Yang, and Parr saw this in the literature and converted it into a density representation to come up with B3 lip. all of this is going to be on your first exam. It shouldn't take more than a couple weeks to study for it. But it's like, okay, you got to hear the words, you got to see the equations. They're on the cluster in terms of the notes. So what are we going to do with this? Okay, and first thing we want to do is we're going to look at obtain a structure for a molecular system. Okay, and so what we're going to do first is going to take benzene and we're going to optimize its geometry. And so what that means is we're going to, basically take a set of coordinates like you've already been playing with quite a bit yesterday afternoon. We're going to add some commands that Gaussian needs to have about it, and we're going to take with a particular choice of basis and a particular choice of functional, we're going to obtain the geometry. So we're going to start off with the guess, and we're going to take the derivative of the energy with respect, not we personally, but Gaussian will take the derivative of the energy with respect to the coordinates, use that to move downhill. The size of the step downhill is based on an estimate of the second derivatives and find the geometry. Once we have that optimized geometry, we'll look at the molecular orbitals and develop these other things about that. Some places, some websites that you've already seen this one. In this website is the instructions on how to submit a batch job to the cluster, and the builder that we're going to use, the location of that is given there. And if you have any questions about Gaussian commands, think that we're going to be doing, there's the Gaussian website. And if you type that in, you'll find that it actually doesn't go there. It gets redirected to a different place. It gets redirected to a Gaussian 16 reference site. For our purposes, the things we're going to be doing, there is no effective difference in terms of the commands. And so this reference is still fine. Okay, then we'll come back to this a little later. Can obtain wave function geometry for your molecule, and so these aren't very big. They're not going to take very long to run, but you still got to build them. And what we're wanting to compare is what we're going to be looking at is the bond angle for water, H2S, and that order. I mean, that's just the way people do it. I don't know. It's a question, I think, of electronegativity difference or whatever. But the series of group 6 elements and the series of group 5 elements obtain those geometries, and there, I guess the P got dropped off. The P that should be there is right there. This isn't PPD, it's PD, it's B3 lip. I like to say B3 lip is like a comfortable old pair of shoes. You know where the holes are, but they're still comfortable, and it's just a reasonable sort of starting point. You remember from freshman chemistry what the bond angle is in water? How about H2S? Anyone? How about selenium dihydride? Okay, not what you tend to have in Gen Chem. And I'm not going to tell you the answer. Okay, we'll come back with the answer tomorrow. How about ammonia? Hmm? If it was tetrahedral, it'd be 109.471, but it's not. It's a little smaller. It's about 106 degrees. How about like pH 3? Okay, so what, I mean, obviously, if the L came back with the same angle, this would be sort of a silly exercise, but they don't. And you might want to, particularly if you're one of the unfortunate ones with a first stroke case that you already know the answer. But if you're one of the other ones, you might want to remember VSEPR, which you got in freshman chemistry, and for use to thinking about unusual structures and so forth, and sort of guess in your mind what you think is going to go on there. Because what we're going to find out is basically VSEPR gets the wrong answer, and compared to experiment, and we'll go through and use electronic structure theory to understand what's going on there in that case. So if you could email me your log file when you're done, then I'll collect that data so we can talk about it in class tomorrow. Okay. And you say, I don't know your email address. It's pretty simple.
I send them. You're CC on some.
I haven't. I think I've been on most of them this year.
You haven't?
Yeah.
I'll send it.
Okay. So just email me the results, and then we'll tabulate them, look at them, and do a little bit tomorrow morning and on that to understand what's going on. The other project that you're going to do is you're going to look at benzene dimer, and there are two, shall we say, dominant configurations for benzene dimer. I will be looking at their structures a bit. One is a parallel displaced structure where it's a pi stacked, the aromatic rings are stacked on each other conformation. The other is a T shape where one of the benzenes is turned around and pointed down. And you remember from your work you did yesterday, pretty straightforward to take benzene, another benzene, and translate it and shift it to get a guess for that parallel displaced structure. The displacement, the distance between the two benzene planes, is basically very much the same as in graphite. It's around 3.5, graphite's 3.4, but 3.5 angstrom displacement, and the downward or upward, depending on which way you do it, shift of about 0.5 angstrom. And so you could add a second benzene, translate it, shift it to get the coordinates for the parallel display structure. T structure, you take benzene and you rotate it around, and then you translate it, okay, to get it pointed up. And there the translation is about 4.6 angstroms. For, gosh, how long? First papers I remember were in the early 80s, about 1981. A controversy developed and arguably is still ongoing in the literature about which conformation of benzene dimer is the conformation of benzene dimer. And there are still, if you went to SciFinder and did a search on benzene dimer, you would find in 2017 still papers where people are arguing about benzene dimer, which conformation is actually preferred. Now, at this point, the difference in energy between the two conformations with the state-of-the-art electronic structure is about 0.01 kcals. Okay, but they're still arguing that, oh, this is better than this. It's like, come on, give me a break. Given the fact that in the real world, it's not really frozen, right? It's rattling around and everything else. Arguing about that is a problem. But, we are going to argue about it because half of you are doing the parallel display structure and half of you are doing the T-shaped structure. Okay? And we'll be able to get at the relative energies of those two structures with these three different functionals. And the PBE, P is Purdue, B is Becky, and poor E, I don't remember his name. He was probably the grad student that really did the work, but he gets none of the name recognition. We saw B3 lip. The next one is APFD, which is Austin Peterson Frisch, and the fourth author, who again I don't remember the poor guy's name. He didn't get a letter even. The D stands for dispersion in that functional, but we'll do those and see how the results turn out tomorrow. And again, obviously, if ever they all gave the same answer, then I would just be sort of, just busy work. But they're going to give different answers. And if your result sort of bothers you in that it goes for a very long time, that's okay. It might take a long time, or it might be done in a few seconds, depending on which functional you happen to have selected. Okay. So, actually, the first thing we need to do is we need to build a molecule. Okay, so if you go to that website, and I'm sure you've got to memorize the path to that site, and actually, I'm sorry. This is the one that's there. Okay, so if you go to that site, the first thing you see is there are several options, different kinds of builders and so forth. What we're going to be interested in is using the computation part, and we're going to use electronic structure program Gaussian. We could also use a different program called Orca. There's dozens of programs out there. Again, Gaussian is kind of like the old shoes. It's got a lot of stuff in it. So we're going to build the, even though you know how to generate the coordinates, okay, and you can use your coordinates that you generate, we're going to use the builder to build the coordinates, save a file, and
I didn't quite get down the address. Okay.
It was so. The type is so big. So cclear, chm, colostate.edu/pay/hydrogen/Perry. And in principle, if you type that into browser on your cell phone, it would also go I haven't tried that recently. Okay, everybody have that? Okay, so we're going to go into Gaussian, and we're going to first build the molecule, and then generate the Gaussian input data for that molecule, and then create the text file, which we'll send to the cluster and run. Okay, so build. Okay, and you start. Kind of sounds like the first thing you should do. If you wanted to grow a bigger molecule, you could append or you could add a molecule. Tomorrow, when we're looking at transition state, we'll go through a little bit more of this functionality. But start, and then a palette of species comes up. The one we want is this one here, which is benzene. And it doesn't, work in progress. It doesn't come up centered in the right size, but when it's talking about drug molecules, these aromatic rings, they play an incredibly important role, and so the default representation actually shows the pi orbitals. You can turn that off if you find it annoying, but that's benzene. Yes.
Is there a way to zoom out? It just went up to find out it's like really.
Yeah. So you want to click in there, and then zoom out.
Scroll.
Scroll.
Oh.
Yeah. Use the.
Okay, and so we got benzene. Now we want to build the input deck for Gaussian, and there's several parts to it in terms of what your the input. The first, and you could basically think about rolling across here for getting at the different command parts, but job type. There, this little arrow, you click on that, and you can do just obtain the energy. So find the wave function or the expectation value of the wave function, derivative expected coefficients, get at the energy. Or you could optimize, or you could do a vibrational frequency calculation, or you could optimize and do a frequency calculation. We're going to just do the optimization because it goes quicker, but you can see there's an arrow on that. So if we select that, then there are under optimization, optimize to A and minimum or transition state, and the parentheses, Bernie. Guy named Bernie, actually, that's just, in contrast to these other things, that's his first name, Bernie Schlegel, came up with this algorithm for finding transition states, which, there are people that buy Gaussian and calculate the energy and the derivatives in their own program, but they run it through Gaussian to be able to do the Bernie optimization. It is the most robust transition state finder out there, and so and so Bernie gets a parentheses on the name. But so we want to do a minimum right now. Tomorrow we'll come along and do a transition state, and basically instead of heading down, we're going to head down in all directions except one. In one direction, we're going to head up. to get to a maximum in that direction. But so we're going to minimize, and that's all out of that. And we can see down here, it's building a command line for us as we go along. Method. Okay. So under the method, again, there's several options. You could do a ground state, you could do a Zendo calculation, a singles, CI singles, you could do a TD, time-dependent calculation, and we're going to just do a ground state. And the method, semi-empirical or molecular mechanics, or Hartree-Fock, or density functional theory, and we're going to do a density functional calculation. More choices. Okay, so default spin. We just leave that alone. We're not going to do unrestricted yet. Then the technical term stuff. It's almost insulting. The choice of function. And see, there's a list, long list of choices, and in fact, there are probably 30 more choices that are available in Gaussian. And those of you who are doing the PB1, PB1, or PBE1, PBE, and it's not there. Okay, but that's okay. We'll get to that. But so the top ones, APFD, LIP, are listed there, and we're going to select. Let's do B3 LIP. APFD is the first choice because that's the one that we tend to use, but we'll go with the old shoes. Basis set. Okay, we didn't go through, because that would be another 20 minutes. We didn't go through the nomenclature of basis sets. The STO is Slater type orbitals, where you take, instead of using Slaters, you fit the Slaters to Gaussians. G is Gaussian. We're going to go ahead and use, I think for now, we'll just go ahead and use this 6-31G basis set, where we said for hydrogen that 4 functions were kind of good enough, but we have some carbons. So we described the 1s of carbon with 6 functions, the 2s and 2p of carbon with 3 plus 1 or 4 functions. Okay? For hydrogen, it would just be 3 plus 1 or 4 functions. And, then there are a bunch of other options out there. So in the homework, it's specified which basis set to use. We're going to use that one and more choices. Okay. So DEF stands for diffuse functions. And so if you're doing an anion, you want the anion to be able to get bigger if it wants to. Okay? This is all obtained variationally. That is, you minimize the energy. And so if it doesn't want to use it, it just won't use it. But if it helps the energy, and anything that lowers the energy is good, right? So it's not that we're adding extra parameters. We're just heading towards the variational best. And so we could add, the first plus is adding diffuse functions, diffuse S and P functions on, say, carbon. The second plus is adding diffuse functions on hydrogen in the molecule. And we're not going to add any of them right now because we're just doing straight old benzene. Benzene isn't a negatively charged species. It hasn't gained a lot of electrons, so we're just going to leave that off. The next is adding D functions. D functions. 2D would be 2D functions. DF would be adding, in addition to a D function, adding an F function. So 3DF, 2DF with 2 Ds, 2 Fs, where we're allowing the shape. Looking for chalk.
It might be in the little box, the green box. The top box now.
So if we thought about in particular, we won't draw the whole thing, let's just consider ethylene. If we think about the 2 p orbitals of ethylene or the 6 pi orbitals of benzene, if we just have a p orbital, then there is a certain degree of overlap between those p orbitals in the bond. If we added a d function, so here we have plus minus, we add a d function on each center, where it's plus, minus, minus. So plus, 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 minus, minus, plus. If we add that p function, then this p orbital is going to sort of pooch towards the bond. It's going to distort towards the bond. This p orbital is going to move in. And so instead of just being straight up and down, they're bent in a little bit towards the other center. And if that increases the bonding, that lowers the energy, that stabilizes the system, and it helps. And so in ethylene, adding this single P function lowers the energy or strengthens the bond by about 15 kilocalories per mole. And so it's fairly significant. One tends to add on these polarization functions. For hydrogen, if you have a hydrogen orbital, again, it can be polarized by adding a P function as it gets pushed out that way. And again, that lowers the energy of the system. It helps. If it doesn't lower the energy of the system, then it doesn't do anything. Okay, so we are, this calculation, going to add a single D function. We're not going to add a P function on the hydrogen. We're just going to allow the pi orbitals to change their shape and then go forward. The next lines are charge and spin. This is a singlet state and no charge. And so that's basically all we need. Okay. So all of that talking got us an oct. It got us our choice of functional, and it got us our basis set. Okay, and we'll see that in the when we look at the VI at the file, we'll see that command line. And then we have this title card line. You have to have a title card line. If you don't have a title card line, Gaussian dies. If this title card line doesn't have enough text on it, it dies. And I don't remember, it's something like 15 characters. If it isn't 15 characters, it dies. And so say something like title card line. Or, heaven forbid, you actually want to be able to look at the output and figure out what it was, you could actually say something like benzene optimization. But we're not. Okay, so now, because this is in a web browser and we don't like viruses, right? You don't want to just randomly, willy-nilly be able to download some or have some software download something to your computer without your knowledge. When we download this file, let's call this benzene. just a little bit more complicated name. Benzene star. And if I can find my cursor, you see that it downloaded it to the downloads folder. That's the only place that you can download stuff, from the web, that without it being a problem. 70 more. Okay. Can I just drag this to your desktop?
Sure.
It's like, if I knew how. Is that the back window?
You just want to do it?
I want to view it and then we'll copy it. Yeah. So if you see here, so it's GIN is Gaussian input file, and this HTML is added on. If you're using Safari as your browser, it adds on this HTML suffix. Any other browser, it doesn't. It just keeps the name the same, but it'll end with .gin. So before we do anything with it on the cluster, we're going to need to get rid of that .html. Okay, so this doesn't look a lot different than what you had before in terms of the XYZ file that you had for benzene that you were spending the afternoon with yesterday. I mean, it's a little bit different. The coordinates are different, but you have carbons, you have hydrogens, and you have coordinates. And then at the top, that first line, the pound P line, the pound is a signal for Gaussian that this is a command line with options. The P says basically just give me a little bit more printout than the default. Then opt is I'm going to optimize the geometry. I'm going to take the wave function opt. If we didn't have opt there, then we would just take the geometry, find the wave function, and stop. But we're going to, we're going to, for a given geometry, find the wave function, then find the derivatives of the wave function with respect to coordinates, step, redo that until it's achieved convergence. Functional B3 lib, basis 631G parentheses D. You can have multiple command lines. Okay. Sometimes this will be, if you're going to add a solvent model, if you're going to do this and that, you can have several lines of command. It's terminated by a blank line. That's why there's a blank line. Then you're going to have a title card, and again, this is just title card line. And then again, you could have multiple title cards if you wanted to. That is terminated by, and I don't know the number. There is a limit to number of title cards, but I mean, if I just use title card line, I'm obviously not the one to ask how many you could have. Blank line. Then this is charge and spin. Singlet is 1. Could have had 0 for 0 unpaired electrons. Okay, that would have been a good choice of number as well. But so singlet is 1, doublet is 2, triplet is 3. Doesn't correspond to the number of electrons, but that's just the notation. Then the coordinates. Okay, and check and see. Yeah, this. There needs to be a blank line, which is the final sort of terminus that we've given it all of the input. So you could well imagine that your XYZ stuff could fit right in here. We don't tell it how many atoms there are in the molecule. Okay, It's just that section of the input is terminated by a blank line. Okay, everybody's got a file? Yeah, I was going to get rid of this first. Okay, so now we want to move that to the cluster. So we're going to take the file and we're going to login one.
RC. Login one. RC.cost. So your username, not.
Yeah, no, I mean you could.
Copy.
Well, you don't want to know my passwords. You couldn't actually successfully copy, but you could potentially.
If you're using a PC here, you're going to use the WinSCP program for this. So anytime he uses the SCP command, you use the WinSCP program to transfer files. So all we're doing is taking this file from the laptop and moving it to the cluster.
Did you take the one off and change that to Colorado? You log into the Summit computer down at Colorado with this thousands of processor system, which coincidentally is not as fast as this for running Gaussian.
Oh, yeah?
Yeah, it's about 20% slower.
In my cluster, in your cluster. Oh, you mean
Your cluster.
Oh.
Mine's actually a little faster.
Yeah, I would have thought so. My processors aren't even that good.
Neither are theirs. I mean, they're good in some ways, but for just this, they're not that good. Okay.
Oh, no, you need to put a colon in.
Okay. So now SSH. So now on the cluster, have this file that we are going to run through Gaussian, and the job that we're going to submit, the script that we're going to submit, is a thing called Gaussian.job, which you should have, right? They should have in
Their day 2 folder on muster.
I guess I should have done that.
But you can do that. So if you just go, is everyone logged into their home directories? If you just type cd muster file system, and then you type ls again, you should have a folder called day 2. Everyone should have a folder day 2 in there. Is anyone having trouble doing that? Okay. So if you, who said yes? Where are you at?
Trying to get the cluster.
Where? Go to your home directory. You just type cd. Anytime you're anywhere, you can type cd and then enter, and you go to your home directory. And then you type cd muster file system, and then return, and you should be in your muster directory, which will be home, your username, muster. You there? Okay. So now there should be a folder day 2 in there. You can go in there, and you should have a file called in green, or called Gaussian cluster.job. And this is an example. This is an example submit script. It hasn't been. Okay, so this is an example submit script to run a Gaussian job. So the important line is this, and anytime you see a square bracket in this example, when you actually run the job, you're going to have to change those 4 instances. 2 instances in the preamble, and then 2 instances in this line that you'll have to change for your specific job that you want to run. In this case, we're running a job called benzene start.gin. That's the Gaussian input file name, and so that replaces including the square brackets. So you've got to get rid of the square brackets, and then here you would just type in benzene_start.gin. This is the name of the log file or output file that Gaussian's going to create. And then these things are just queuing system information, but you should change them to, actually in those cases, it doesn't really matter what you change them to. You can change it to whatever you want.
Okay. And you can use, shall we say, acceptable names are gin or com. That's what Gaussian likes to use, and out or log for the you know, and it doesn't matter. I can't remember what I used for like. It's another set for like 20 years until I finally caved in.
Takes a little second.
Yeah.
So, well, for some reason, I don't understand why on cluster when you're in the Lustre file system, it takes the time to write a file for some reason. But that is the reason for that. The reason for having the Lustre file system is so that this is the hard drives that are mounted by all the nodes. So you actually have to run all of your jobs from the Lustre file system. So anything you should create any directories and such that you're going to submit jobs, which is what he's going to do now. You should do under the Lustre file system, as opposed to your home directories.
Okay, so now I just copied my file. There, we have the submit script. And you see there's a couple of other files. These are pre-made benzene dimer structures. If after a little while you get tired of trying to build it, you can basically get those and use the coordinates from there. Okay, so now it's S-batch. And one of then on the Fixman site, down at the bottom, there's a file or a web page, a link that talks about submitting Gaussian jobs. And do I need the .job, or is that? Okay.
Yeah. You need the whole file.
So S-batch, file name. It's gone off. We're going to go through and determine from our starting guess march downhill until it finds the, the derivative of the energy with respect to coordinate being sufficiently small, and decides it's done. Okay. So we got a file back called benzene start.log. Maybe a little small, but, or is it still going? Because all of the
still
temporary
running.
files are there, so it's still running. Okay. I get, don't like just sitting around, want to see things, even if it's not really helping anything. And so I'll look at the log file while it's running. Except if I did VI, then I would be opening it for writing. And the next time Gaussian went to write, it would kill it. And so view is a read-only version of VI. And so even though it's still going, we can.
It's done now.
Okay. So opening the file in VI, see a lot of stuff going back to Gaussian 82 in 1983. Gaussian 80 was free, but starting in 82 and going forward, they have gone commercial with it. But so that's there. They talk about that this contains proprietary confidential information, including trade secrets that belong to Gaussian, and they take that seriously. There are people who have been banned by Gaussian. Their institution can't buy Gaussian if they're considered a competitor or if they did something that they weren't supposed to do. We're not. Yeah, so then there's this warning, can't be used anyway to compete with business model of Gaussian, blah, blah, blah. Citation. Just wonder how much space is taken up on the internet with that text. Okay, so our lovely little command line, right there, puts it out.
How is it that you ran it again? Because it was freezing up when I got it.
S-batch space and then the submit file.
Do you have to be in the same directory as the file? Or?
Yeah, so you
I just
go to your
Believe it or not, this stuff actually means something, and it's telling it which programs to run when, in what order, and what options. I have never had the need to create that, but you can create yours and run something special there. But so then here's my title card line, which would otherwise summarize what the molecule is. Coordinates, as we inputted them, gets paired out so that you can see, what you did. turning on that P gets you some extra things. So this does the optimization in not in terms of XYZs, but it does the optimization in terms of bond distances, bond angles, in what is called a redundant set of internal coordinates. But so the initial starting guess is the carbon-carbon, the CH distances, the angles. This is what the initial input was. So distances, angles, dihedral angles. If your molecule gets a little bit bigger than that, it doesn't print all that out anymore because it's too much. Again, this is the input orientation. Gives you information. Sometimes if your job goes bad and you have two atoms that are too close together, you can look at this distance matrix and decide, okay, that's what's wrong with my structure. And it does, if you were to compare the input orientation to the standard orientation, it changes things around. It uses its own preferred coordinate system, which is a rotation and translation away from your coordinate system, unless you've basically adopted the standard orientation previously. Tells you the number of basis functions, number of alpha and beta electrons. Okay, so these coefficients, these basis set expansion coefficients, you got to have a starting guess. And so it goes through and generates a starting guess for the coefficients, gives you an energy, an error, and it then makes a step down in energy in terms of the expansion coefficients, not the coordinates. Second step, third step, you can see that the energy in Hargreaves is going down, the change in energy as it's carrying out the optimization. And I mean, 99 times out of 100, you don't actually look at this stuff. It just, we're just going through it once it's done. So it's found the total energy here after 11 cycles. It has its convergence criteria as to deciding that the change in the energy, the change in the coefficients is sufficiently small. Then it gives you the orbital energies for the occupied orbitals and the orbitals that aren't occupied. Gives you estimates for partial charges. Then it figures out the derivatives, the forces. Does an update, figures out the step size in each of the coordinates, makes a step. I started off from a guess that was fairly close. So these derivatives are fairly small. Again, updates the coordinates. Redoes the SCF for the new geometry, forces, step, and says that the criteria on force, criteria on displacements have been met. It's found the geometry, and it has the new optimize distances and angles. Just that's information. And, you know, if you, most of the time, if you're going to look at the output, what you'll do is you'll skip down to the bottom. There's always a quote at the end of Gaussian. If it ran correctly, if it didn't, you get a line that says L999, which means it's an error and it didn't run. Never found the file with all of these in it, but there's a file somewhere with all of these quotes. And there are probably tens of thousands of quotes. Okay, so that ran. So now we have we have our log file that we looked at, and I forgot to add one thing at the top. So the log file gives us the final coordinates for the molecule. It gives us information about the wave function a little bit, but it doesn't have the whole wave function. It doesn't have the coordinates in a precise way. That information is stored in a thing called the checkpoint file, and I forgot to name the checkpoint file. And so at the end of the job, that information got wiped out. So I'm going to need to rerun it, unfortunately. And as will you, if you want to run these other jobs. So you want to put a line at the top, percent check equals, and you don't have to give it the same name. It's just a whole lot easier if you give it the same name in terms of keeping track of all your files. So we have benzene goes for start.check. So now when it's running, it's created this other file called benzene start.check, which has more information in it that we're going to want to use. Okay. So what we're what we're going to want to look at is is some of the molecular orbitals, and to do that, what we're going to do is generate a cube file where at a grid of x, y, and z, we're going to evaluate the wave function or a specific molecular orbital, evaluate the value of that at that point, and build this box which we'll display back on our local computer. We're also, in addition to doing the molecular orbital, we're going to want to generate the electrostatic potential, and we're going to want to generate the total density, and take all three of those files back. Tomorrow, when we have a system with an unpaired electron, we're going to want to generate a spin density plot as well. But for now, you have a folder are a directory underneath there called scripts. And inside there are a series of scripts. Let's go ahead and go there. And these scripts are for, calculating the electrostatic potential, for calculating the total density, for calculating the spin, and some other things along the way. We're going to be doing AMO for alpha molecular orbital, and then we'll be running the TDEN and ESP. All of those, because typically one does this sort of analysis on a different computer, all of those use a formatted checkpoint file rather than the checkpoint file, which if you were to open in VI would just be a whole string of stuff that would make a mess, probably freeze the VI session, because it's not printable characters. Okay, so back up. Scripts. So I'm going to run the first one is going to be generating the formatted checkpoint file. So that, and then start, or then the file name. If you didn't give it enough arguments, it'll come back and say that you're missing something. This one, there's only one argument, and that's the checkpoint file name. Okay, so it read the checkpoint file, wrote a formatted checkpoint file, and messed around a little bit with the coordinates. So now if I do AMO to plot alpha molecular orbital, it says you got to give it a number because which one, and I did. So how many electrons are in benzene? So 6 per carbon plus 1 hydrogen, so 7 per times 2. No, excuse, times 6 is 42. 2 electrons per orbital. So the HOMO, the highest occupied molecular orbital, is going to be 21.
You don't have to give core electrons in
6 should be the core for carcinoid.
Oh, yeah.
If you get into a more interesting molecule and you don't want to count up the electrons, if you search for the string alpha, it tells you 21 alpha electrons and 21 beta electrons. Control. Okay. So, for benzene, these are the orbital energies. So the 1s, so 1, 2, 3, 4, 5, 6 1s's, and then CC and CH bonds and so forth, all the way up to this orbital as being the highest occupied orbital. And we see its energy is 0.246. This is 0.246. The degenerate set. When we look at it, we'll see it's an E, and we'll see it's a pi. And then, because you have all of these, you can go back and look at them. If we were then to plot the next one here, we'd find it's not another pi orbital. It's a sigma orbital. So we need to march back through to find the A1. So we have A1 and then E for the pi orbitals. The empty orbitals, these would be like the pi star type orbitals. For now, we're just going to plot, look at a couple of them. You could take this and look at more. And when you start thinking about excited states, you're going to want to look at more of these. Okay. So back there, 21 was the HOMO, 20 was HOMO minus 1. Actually, okay, so that in this universe, 1 is 2 electrons. I don't know why they could have said, but so electron sum here is a half. There's 1 electron in that orbital. Because we have both alpha and beta. There's 1. It's just telling us, okay, that is a okay. So now we have 2 new files created that are the 20th, 21st alpha molecular orbital, .cube at the end. 3-dimensional grid values of the orbital over that 3-dimensional grid that we can look at. So is it going to be easier to SCP from here back to you, or to go there and SCP from probably easier?
You have to be on the laptop. Just keep that open.
Okay, you got that? So he did an SCP from where I had, and so for you, basically it's going to be the same, except
You guys want to use WinSCP probably. When you're on a PC.
Okay, you're gonna just transfer the files, cube files back to your local machine.
so back on your local machine in the browser, we went back to the starting point for this Perry, and now we're going to go to cubes instead of the computation. We're going to go to cubes to be able to display the cubes. And so we're going to input output. We're going to load a local file. We're going to browse for the local file. And
Desktop. I just copied them to the desktop.
so then we select a file. out. Nothing's displayed. Yep. So this is a grid, and we're going to generate a single value of the wave function for our three-dimensional plot. And so like 0.02. Okay, I didn't like it there. Well, that's a drag.
You need to give it a name.
Well, I thought I got it from down here. I think that's for the finding it on the server. It's just a different. Well, thankfully we're out of time. Okay, so tomorrow we'll go through your results. We'll also go through like displaying some other things and build a transition state. So I should do one more thing before we're done. Okay, so some of you are going to be doing, say, like ammonia. One of you is going to be doing ammonia. And so to do ammonia, you just click on ammonia, kind of hard. This lone pair thing is actually the NBO analysis lone pair, but that has nothing to do with what we're after. But let's say you wanted to do, instead of ammonia, you want to do arsenic. Let's change atom. Okay, and so now instead of having ammonia, you've turned it into ASH3. You save the file, upload it, do the various things, optimization on that. Okay. If you have any questions, any problems this afternoon, in terms of if you use your coordinates for benzene dimer, you just need to replace the coordinates part of the file. This top part in terms of what you do, you can, basically do the same except for you need to change the functional. And I had chalk. Inside the builder, they have PBE, just insert a 1. And believe it or not, it actually makes a difference in terms of without the 1, it doesn't have any exact exchange, but with the 1, it does. And so it's give you significantly different answers. Okay, from 2 to 4, I'm going to be in an oral exam, but I should be in my office the rest of the time. It's on the first floor, just around the corner from where most of the offices are. Other questions?